Alright, hello everyone and welcome back to my R tutorial series. This episode marks the beginning of a multi-part lesson where I begin to expand on our basic knowledge of R that I went through in the first 5 episodes to produce actual results in an applicable field. So this lesson, each of the videos therein I should say, is going to go through a generalized statistical workflow for testing the differences between two or more groups in a dataset. So this could be anything from testing the effectiveness of a new medication by comparing a symptom between people that took the medication at certain doses and those that didn't take it. It could apply to testing a difference in the growth of an organism based on whether or not it was supplied with excess nutrients or put under some form of stress. There are a lot of possibilities for this workflow. It's pretty malleable, it's pretty simple, and depending on your data and your questions, there are a lot of different things you could do with it. Now, throughout this, please keep in mind that I'm not a statistician, and I did learn most of this from my bioinformatics class that I took in undergrad. So most of this is just coming straight from that class, and my statistical knowledge on some of these things may not be perfect or complete. With that, I would also advise, if you're a brand new beginner to R, to make sure that you've seen my first 5 lessons before starting this workflow, because I'm going to assume to some extent that you know some of the lingo and some of the shortcuts and commands in R and how the code is written. So make sure that you have some knowledge of that before following along with this lesson. So let's jump in and start by discussing the data. Now, there are a number of built-in freely accessible data sets that R and other packages in R provide. So I'm going to use one of the simpler ones from base R called chick weights. Note that there are 2 different chick weights. There's one with weight actually spelled out, and then there's one with chick WTS, and that is the one I'm going to use. To get to this, we need a chunk, and in that chunk, we can use the data command, and we just need to know what it's called. So we want chick WTS. Okay, and that opens up the chick weights data, and it also gives you the chick weights data as a data frame. So you can also put this in quotes, and then you can call it differently. Doesn't matter if it's in quotes or not. I thought it did at first, actually, but it does not matter. So now that we have this, what is it? So this is just 2 columns, weight and feed, and 71 rows of data. Basically, these scientists, whoever they were, took a bunch of baby chickens that were 6 weeks old after having fed them these dietary supplements. There's 6 different supplements, and they fed them these supplements for 6 weeks, and then they measured their weight in grams. Now, there's no before and after, it's just this one measurement. There's no time scale other than they're all at 6 weeks of age. So it's not the most interesting data set, but it is useful for basic statistical analysis and kind of practicing with R. There's a whole bunch of other data sets that you can use as well. If you want to read more about it or any of the other data sets that we have, you can do a double question mark down here in your console and then search chick weights. And over here in your help pane, it pulls up the link here and you can read about it. There's formatting. It explains, usually they explain what their variables are, and there's some details and some references. So pretty useful little feature of R to have all this data built in and shared freely. So the next thing we should do is define our analysis before we get started with it. And in this case, I'm just going to go through a very basic classic statistics p-value based, null versus alternative hypothesis based tests. So, of course, p-values are not perfect. They're not the gold standard anymore as much as, say, effect size, but we're going to use them for this because I'm just trying to keep it simple and go through some of the more common basic p-value tests. So I'm going to test for the difference in the weights of chicks, starting with just the first 2 feed types, And then I'm going to test for a significant difference between all 6 of the feed types. And so to do that, we're going to start by checking for a normal distribution of the data. So before we can do that, though, let's separate out just the first 2 feed types. That would be horse bean and linseed. I'm going to separate those from the rest of them just because the other ones will start to get in the way. So to do that, we can do our good old-fashioned subset command. I'm just going to call this chicks1. We'll do subset, the original chick weights. Subset is going to be parentheses. This is a good place to use the match operator because we have 2 different feed types. So feed needs to match with %in%. And we concatenate horse bean linseed. And there is our subset. So now if we look at chicks 1, it's only 22 rows and it's all just the ones fed horse bean and linseed. We can also go a little step further and take the weight out as a vector of its own because we only need that to do the statistics and normality tests. So I'm just going to call this WTS. And we're just going to use the very basic shorthand, as I like to call it, R shorthand. Chicks1, $weight. Now we just have a numeric vector of 22 items that are all just the weights of the chicks in this subset. So now that we have that, let's take a visual approach first by making a QQ plot. So in a new chunk, we just need 2 very simple lines of code. One to generate the points. That's going to be QQ norm. And we just give it the weights data, just the numbered data. And then we also use QQ line, and that generates the line for the plot. So if we run both of these, we get this normal QQ plot. Now, again, I'm not a statistician, and I don't really thoroughly understand how QQ plots are developed. However, I do know that the closer these points are to falling on the line, the more normally distributed it is, or the higher chance it's going to be normally distributed. The tails being a little further off, either near the bottom or the very top, is okay. That's pretty normal. This looks decently normal. It's not bad. I've definitely seen a lot worse. So there's another visual way to do this. We could do a histogram. So to do a histogram, you just use the HIST command, the hist command, and we just have to give it at least a couple arguments. X is going to be what you're making a histogram of, so that's just going to be our weights, WTS. And then we need to tell it to give us the density instead of the frequency. So FREQ needs to be false. Just be capital F or the full word false in all caps. And that basically, the y-axis in this case will now be density. If we left this as true, then it would give us frequency. So when it bins our weights into different groups, frequency being true would say, oh, there's this many data points that fall in each bin on the y-axis. Whereas if it's false, then we get density, and I'm really not certain how density is calculated for this. But it gives us a very small decimal number, which you'll see in just a moment. So the other couple things for this, we're going to give it a title, just for clarity. I'm just going to call it chick weights. And so a main title on a plot is going to be main in most cases. And then we can give it a new x-axis label with the xlab argument. And this is just because the X label in this plot is probably going to be a little weird. The Y label is fine, so we don't need to change that. So I'm just going to set this as weight in grams. Or you could also call it mass, I suppose. And then one last thing, we do need to change the Y limits, the limits of the Y-axis. I like to make it so that all of the bars on a histogram are within the whole plot, and we have an even distribution of tick mark labels. So in this case, I've seen this plot before, and I know the limits that we need. Normally, you would have to run the plot and see what it looks like, and then you can change this. But I'll just have us do it now, just so it looks a little nicer. So y lim for y limits. Now you can do this with x lim as well for the x-axis, and this just takes a two-piece numeric vector of the minimum and maximum. You just need to concatenate it with the C command. So our minimum is going to be 0, and then our maximum with frequency set to false needs to be 0.008. Now the real maximum is something like 0.006 something. But then it shows it as like 0.007, and the bar goes slightly above the actual top part of the axis, and it just looks a little weird to me. So that's all we need to generate the histogram itself. So here's what that looks like. And you'll notice it goes all the way up to 0.008. This bar just goes slightly above 0.006, and if we had left it, then it just stops it here, and then the bar is above the axis, and I just personally don't like that. You'll notice it named it density for us on the y-axis, so that's why we didn't have to change that. And our weight label is down here, and our main title is up here. That's what we want it to look like. There are plenty of other aesthetic changes to make too, by the way, but I'm going to go through all those in a separate episode where I talk about graphics in R. There's a lot more to go through, and I just don't have time for it in the statistical workflow lesson. So before we move on from the histogram, I always like to compare a histogram of data to a projected normal distribution of said data. So we can do that by generating a normal distribution curve on top of this. And we need two things to do that. First, we need a sequence of values on the x-axis that range from the minimum and maximum of the actual data in small intervals. And the smaller the interval, the smoother the curve is going to look. So let's make that first. I'm just going to call it xvals. It's the values of the x-axis. And we're just going to make a sequence with the seek command. And this just takes a couple of arguments. We can use from to tell it the minimum value of the weights data. Then we can use to. That's the maximum of the weights data. This is just where you want the sequence to start and end. And then there are two options here. Now I was using length, which defines the number of points to generate. But last time I tried this, it actually gave me an error. I'm not sure if I did something wrong or if the code is becoming deprecated with the new updates. So I'm just going to use by. Length tells you how many points to generate at even spacing in between your from and to values. By lets you define the interval. So how far apart do you want the points, and it will use that to generate whatever number of points is required for that. Now I think the caveat to this is you need to give it something that is an even interval between your points. So it doesn't have to be a specific number of points, but it has to be divisible by the range of your data. So the minimum of our weights data, if we just run that in the console, is 108, and the maximum is 309. So if we do by 0.5, that's something like 400 points in the curve. That should be fine. That should be plenty. And then we can close that off. And that will just generate a vector called xvals. Yep, 403 points that are evenly spaced from 108 to 309 by 0.5s. Then we can use that to generate a line, and we need the lines command. Note that there is an S on this one. There is a command that is just line. It's different, and I forget exactly how it's different, but I know we need the S in this case. So lines, and this is actually a type of plot function, so we don't need to define it as an object. We just need the lines function, just like the hist. And this, if you expect it to plot, I don't think this will actually run on its own. I think you need to generate a plot first either with hist or with the plot command or something else. But we want to put it over top of the hist anyway, so we'll just run this whole chunk when we're done. So lines just needs x and y values. The x will be our xvals vector, and then y, we need to generate a normal distribution based on these x values and the summary statistics of our actual data. So we're going to use the dnorm command, which generates a normal distribution of values. The x argument within dnorm is also going to be xvals. And then we need the mean and the standard deviation of our data. And that's very simply, the mean argument is the mean of WTS. And then the standard deviation is just SD. That is the SD of WTS. And then we can close all of these parentheses. There's 3 total there at the end. And we can run this whole chunk again. Now we have a bell curve that illustrates what this histogram should look like if the data was 100% perfectly normally distributed. Of course, it doesn't have to follow it perfectly, and it does a decent job. It's a little off over here on the left and in the middle, but it's not terribly far off. Again, these are very small intervals here, so I'm not really sure exactly how that's scaled, but the reason we use density is because it doesn't display right if you use this format of the lines code for the normal curve if you do frequency instead. There probably is a way to do it like that, but I am not aware of it. So now that we've visualized the normal distribution of our data to see if it is or isn't normal, now we can actually find out with p-value tests, normality tests, I should say, p-value based normality tests. So to do this, I have a chunk of code that I've been using forever. And that's the nice thing about code. Once you learn how to organize it in a way that works for you, you can save it and then reuse it and reuse it and reuse it. I've had this code for well over a year now from my bioinformatics professor, and it's a very useful chunk of code because the nice thing about this is it will allow you to run a whole host of normality tests. We actually run 6 of them at once, and it displays it nicely, so you can compare them. Now, what I didn't do earlier, and I'm just realizing this, is I didn't define my statistical parameters for how I want to go through this workflow. So let's do that now before we actually get into the statistics. And the first thing we should do is define our alpha, which is our p-value significance threshold. And I usually just say 0.05 unless told otherwise by like a paper on a test or something like that. Like if you read an article, sometimes they'll give you an alpha value that they recommend. But in most cases, most people just use 0.05. That basically just means that if the p-value is greater than that, you can't conclude that the data, you can't reject the null hypothesis. And now, what is our null hypothesis for the whole data set, or for the whole workflow? That is that there is no significant difference between the weights of chicks that were fed horse bean and those that were fed linseed. Just for these two. That's our null hypothesis. We're trying to see if we can reject this. And our null hypothesis for a normality test is that the data are normal. The data are normally distributed. So basically, if our p-value is greater than alpha, you can't reject the null hypothesis, and you do not have enough evidence to conclude that your data do not follow a normal distribution. So, yes, I spelled that wrong. So if the p-value is greater than 0.05, or alpha, then that means that we can't conclude that the data are not normally distributed. So it's a little confusing because with null hypotheses we have to use like double negatives usually. That's just kind of the convention. It's another good reason to use alternative competing hypotheses, but right now we're just trying to keep it as simple as possible. So my code for this requires a package called nortest. You may need to install it. I'm going to call it with library. It's NOR test. So again, if you don't have this installed, just to remind you, you can do, in the console, you can use install.packages, and then in quotes, nortest. Or you can quite simply go up to the Tools tab at the very top, and then the first option, install packages, and then just type in nortest in that second box, and then run it. So I'm going to call nortest with library. Once you install it, you'll still need to call it with library or require, just so you know. And then, so again, once you've got your data kind of organized from a while ago, you can save it and reuse it. So I have this already typed out. You may need to pause the video to actually type it if you're following along with me. But here are our tests. This first thing is just a character vector showing the names of the 6 tests that we're going to run. So I'm just naming the tests first. So it's just 6 common normality tests. I think the Anderson-Darling is probably the preferred one. It's probably the most robust. But these are all fairly common in the literature, or at least most of them are. And then we're going to make a new vector called results. And this is where we basically run each of the tests, and we're assigning them using the assign function. So we're going to concatenate this first. We use the assign function, which basically takes a value and assigns it to a character or a string. So in this case, ADVL, or no, I think it's a 1. I'm trying to type out my old code. I'm not sure why we named it this in the first place, but yes, ADV1. And then comma, and we run the test. So Anderson-Darling tests command is just ad.test. Run it on our weights data. Close that second parentheses, and then before we move on, we use brackets 2. So to break this down, and I'm going to get the rest of this in here actually for all 6 tests. Okay. Oops, that's not what I wanted to do. I'm a little OCD about this. So basically what this does is this assigns each value of this vector results this name, and it runs this test on our weights data. And this 2 is here because each test gives you multiple results. So it gives you a p-value as well as some other information that comes out of the tests. And 2 is the p-value. So that's the second item in the results of this test, whatever kind of object this produces. So the 2 is just there because we only want the p-value in this case. You could just run ad.test on weights by itself and see what it gives you. But I like to run these all at once, get the p-values, and then we can use this last little bit of code to make it look visually pleasing, but also nice and concise. So we're going to make a data frame, but we're not going to assign it to an object. That will simply print it below. You can save it as an object if you want and then look at it in the viewer. That works too. But I'm just going to print it as a table. And you'll see that p-value is actually a column in the data frame, and we're actually using an equal sign here instead of the assignment operator, and that's because we're just viewing it, but we're also making it as we go. So I think this is one of the few times where you would use an equal instead of the assignment operator. So the p-value, though, is basically an unlisted version of this, because this results, it's not really a vector, it's kind of a list, I believe, because we're assigning everything. So it actually makes it into a list of single test results, which each have multiple items inside them. So we need to unlist the results because we're only saving the second one, and it can be basically converted into a vector with this unlist command. You're basically converting a list into a vector of each item from each part of the list in order. So in this case, it's only one item because we're only saving number 2, the p-value. So forgive me if that was a little confusing. Lists are confusing in general. I might go over how they work in a broad sense in a later episode, but I'm not sure about that yet. And then just to finish off, we're naming the rows of this data frame, which we'll see in a minute, as the names of our tests. So that's why we made that vector. So that's all we need to run all of this. If we run this whole chunk, now we get this nice list of tests and their p-values from our weights data. So all of these are pretty significantly higher than our alpha value. The closest one is chi-squared, and that's still a 0.1 greater than 0.05. So I would say that we cannot conclude that the data is not normally distributed. Therefore, we are going to assume that they are. Can't technically prove it with a p-value, but we're going to assume that the data in the weights subset that we've made is normally distributed, and therefore we can check for the variance of equivalence, or I should say equivalence of variances, and then we can run parametric statistics, which I will go over that in the next episode. I'm running out of time for this part, so keep an eye out for part 2, and I hope this has been helpful. Thank you for watching.